So we can do this by modifying the list component sizes algorithm from the previous example. So we'll call the algorithm check connection, and it takes the graph, but it also takes v1 and v2. It's going to do something similar to before. It's going to start off with the assumption that none of the nodes have been marked so far as reachable. Then we're going to call marked component on that graph, and the node that we're going to start marking from is v1. And what that's going to do, when this returns, it's going to return a number, but we're just going to ignore it. It's going to go through, starting at v1, and mark, like basically touch every node that can be reached from v1. And we want to find out whether or not there's a connection to v2, and that's really easy at this point. The answer is v2 in. So what this does is it checks whether the node v2 that we've been given as input was one of the nodes that got marked when we were spreading things out from v1. So it starts at v1, spreads things through the graph like some kind of an infection or a good idea. And when that's all through, all we have to do is look to see whether v2 was one of the things that got infected in the spread. So according to this, A and G are connected. Let's take a look back at the graph. G is reachable from A, but that's not so exciting to think about because they were pretty much connected directly. Let's try a more interesting one, say H and B. So it realizes that H and B are in fact connected, and that's more interesting because it requires multiple hops to get from one to the other. And then finally, we can do A and B. We know that they're in different components because remember there was component A with 4 nodes and component B with 4 nodes, but let's make sure that the program can figure that out. Yes, indeed. So when it spread things out from A, reached everywhere it could reach, B was not among the visited.